We are going to continue talking about probability today, starting off with the probability of unions. Do you remember from the previous lesson what the union of two sets is? The union of two sets is everything in one set or everything in the other set. So everything in multiple sets could be in one or the other or both. And the word or is usually associated with unions. Let's look at this first example before we look at what is up here. A fair number cube is rolled. It has numbers 1 through 6. What is the probability that the number rolled is either a 3 or, we see the word or here, a 4 on the first try? It could be a 3 or a 4, so this is a union. So let's think about if you roll a dice, there are 6 possible outcomes. And if we're looking for a 3 or a 4, how many of those 6 outcomes is it? That would be 2 out of the 6 possible outcomes. So what would the answer be? If you reduce 2 over 6, that's the same as 1 over 3. Remember, you could press Math Enter Enter on the graphing calculator to have it reduce a fraction for you. Now what we're going to look at is another way that I could have gotten that to 6. And that is by using this addition rule. We'll come to this in just a minute, but we're going to use this addition rule, the probability of A or B. So let's look at the probability of drawing a 3 or a 4. And what I could do is I could look at the probability of drawing a 3 and I can add it to the probability of drawing a 4 and see if we get the same thing. So the probability of drawing I meant rolling a 3. The probability of rolling a 3 if you have 6 sides would be what? That would be 1/6, or the probability that you roll a 4 would also be 1/6. And does that give us the same answer? Yes, it does. So to find the probability for an or statement, we just add the probabilities together. But that is only if we have what's called mutually exclusive or disjoint events. Mutually exclusive events are events that have no overlap. So remember, overlap would be like this in the Venn diagram because they cannot happen at the same time. So if you roll a dice, you cannot get a 3 and a 4. The other example in a deck of cards would be drawing, if you draw one card, a king and a queen. If you draw one card, there's no way it could be a king and a queen. But an example of mutually inclusive events, not mutually exclusive or not just disjoint, would be drawing a king or a diamond. Those can happen at the same time. You could draw a card and it could be a king and a diamond. So what we're going to have to do, you'll notice that this looks the same if they are mutually inclusive. The only difference is you have to subtract the overlap so that you don't count it twice. You'll see what I mean in just a minute. So what is the probability of drawing a king or queen? This is my example that is up here. If we draw one card from a standard 52 card deck. So we're going to find the probability of drawing a king or a queen. And the way we could do that is find the probability of each of those and add those together. So let's find the probability of drawing a king and the probability of drawing a queen and add them together. So the probability of drawing a king out of 52 cards would be, how many kings would that be? That would be, there are 4 kings in a deck of 52. What is the probability of drawing a queen? There are also 4 queens in a deck of 52. Okay, so see if you can find what that probability would be. You should get A when you do that, because there would be 8 cards in a deck of 52 cards that are a king or a queen. It could be one or the other. There's 8 possibilities out of 52, and that is about 15% or 0.15 if you divide that. Now let's look at the mutually inclusive one, which is drawing a king or a diamond. This one's a little bit different because they can happen at the same time, and we don't want to count anything twice. So let's find the number of cards that are a king or a diamond. Okay, how many cards are there that are a king? There are 1, 2, 3, 4 kings. And how many cards are there that are a diamond? There are 13 that are diamonds. However, we have already counted the king. We don't want to count that one again, okay? So in all, that would be 4 plus 12. That would be 16. There's 16 if you count everything I highlighted, 16 out of 52 cards. Let's look at how we would do this with the addition rule. The probability of A or B, so let's say the probability of a king or a diamond, is equal to the probability of the first event plus the probability of the second event, but we need to subtract the overlap, and that is subtracting the probability of a king and diamond. The probability of drawing a king, there are 4 out of 52. The probability of drawing a diamond is 13 out of 52 because there are 13 diamonds. And then we're going to subtract the overlap. How many events are there in the overlap between the king and diamonds? That is 1 out of 52. All right, so what do you end up getting? You end up getting that there would be 4 out of 13 because if you divide both of these by 4, that would give you 4 out of 13. So you should see we get the same thing if we just add everything and subtract the overlap. We're going to do plenty of examples. Number 4, from a survey of 100 college students, a company found that 75 students live on campus, 45 own cars, 35 live on campus and own a car. What is the how many students live on campus or own a car? So we're going to ask ourselves if this situation, the events living on campus and owning a car, would be mutually exclusive or mutually inclusive. Is it possible to live on campus and own a car? Yes, it is. As a matter of fact, there's 35 people who do both. So that means these events would be overlapping circles because there are people who own a car and live on campus. So we're going to use the mutually inclusive probability here for union with the or. So we're going to find the probability of living on campus or owning a car, so that could be one or the other. That's going to be the probability of living on campus. We're going to add the probability of owning a car, but then since we have some overlap and we don't want to count them twice, we have to subtract the overlap. I'm just going to write overlap. So see if you can find, and actually I wrote P for probability, but we're actually not finding the probability here. It's just finding the number of students. The number of students who live on campus, the number of students who own a car, and subtract the overlap. What would you get? So there are 75 students on campus. There are 45 who own a car, and we're going to subtract the 35 that own both because they are already counted in these numbers. And we get that there would be 85 students in those categories. So that means there's 75 people who live on campus. There are 45 who own a car, and we want to know how many in those group, how many are there that own both. Okay, so that would be the 35 it tells us in between those. So we had to subtract those so it wouldn't be counted twice. Number 5. Consider a spin on the spinner below. We want to find which events are mutually exclusive. That means they could not happen at the same time. See if you could decide what that would be. Landing on an unshaded portion, okay, so that means one of these, and landing on a 2. It's not possible to land on a unshaded portion and a 2. So those would be mutually exclusive. Landing on a shaded portion and a 3. Is it possible to land on a shaded portion and a 3 in one spin? No, it's not. Landing on the shaded portion and an even number. It is possible to land on this 2, and that would fall into both categories, so that would be mutually inclusive. Landing on an unshaded portion and a number greater than 3. It is possible for those to happen at the same time. If you land on this 4, that is unshaded and greater than 3. And landing on a shaded and unshaded portion is not possible. You can't have both of those at the same time. Those are mutually exclusive. Same thing here. Let's figure out which events are disjoint. What does disjoint mean? That's another word for mutually exclusive, meaning it cannot happen at the same time. Figure out which events are disjoint. The events A and B are disjoint because it is not possible to spin a 3 and even number in just one spin. Okay, if you spin a multiple of 3, you could spin a 3 or a 6. It's only going from 1 to 8. So if we're looking at our even numbers, that would be 2, 4, 6, and 8. Spinning a 3. Spinning a number greater than 2 would be 3, 4, 5, 6, 7, and 8. So the ones that could not happen at the same time would be A and B. The others could happen at the same time because they have some overlap. Let's look at another example. We're looking at an airline gathering data on late departures, early arrivals. It says the probability of a late departure is 12%, early arrival is 27%, and we want to figure out the probability of a late departure and early arrival. It says it is possible to have them both happen at the same time. That is a 4% probability. So since they can happen at the same time, they are not going to be disjoint. It's going to be mutually inclusive. See if you can find the probability of a late departure or early arrival. Okay, that is going to be C, because late departure is 0.12, early arrival is 0.27. We subtract the 4, the overlap, because 4% of the time it would be late departure and early arrival, and those are already counted in these numbers. We don't want to count them twice in both groups. All right, let's do another one. 32% of families own a goat, 41% own a dog, and 24% own both types of animals. Okay, if a family is chosen at random, what is the probability that it owns either a goat or Remember that keyword or. We see that 32% of families own a goat, so that would be 0.32, and 41% own a dog. So that's the probability of owning a goat or a dog. However, some of those people are counted twice. There's 24% of the families who own both. We need to subtract the overlap. And when we do that, that gives us 0.49. That would show us all the people who own a goat, all the people who own a dog, the people who own both. We don't want to count twice. Let's do some more. The spinner is equally likely to land on any of the 6 sections. What is the probability that the spinner will land on a number greater than 4 or, so again there's that or, that means it's a union, or on a shaded section? There are 4 possibilities out of the 6 that it's on shaded or a number greater than 4. We could also include the 6, so that's why that would be 4. Okay, a restaurant served 42 customers, 30 ordered a sandwich, 16 ordered soup, 10 ordered both. What's the probability that a customer ordered a soup or a sandwich? Okay, you should do the 30 out of 42 plus 16 out of 42, and then subtract the 10. That would be the overlap because they would already be counted in one of those groups. Let's do another one. The probability that this flight will be late is 0.27. The probability that this flight will be late is 0.11. Both flights have a probability of being late of 0.09. What is the probability that one or the other will be late? We would add the probabilities together and again subtract the overlap so that they are not counted twice. So 0.29 would be the probability that either flight would be late. And let's do one more like that. See if you can answer this one. This one would also be C. We would add the probability of each of them and subtract the overlap, which is 15%. So to find the probability of unions, which would be saying, they usually say or, the likelihood of one event or the other. It could be both. It could be just one. You have to ask yourself if it is mutually inclusive or exclusive. And if it's mutually inclusive, they can happen at the same time. You've got to make sure that you subtract any that fall under both categories so you don't count them twice. If they are not mutually inclusive, meaning they are disjoint, then you just add the probabilities together. You don't have to worry about overlap because there would be no overlap. Next, we're going to talk about two-way frequency tables. Two-way frequency tables show frequencies using 2 different categories. So for example, the categories here would probably be gender. Categories here would be maybe where's your favorite place to vacation. And then there are frequencies for each of them. Okay, we'll talk about a relative frequency table in a minute, but let's make sure we know how to interpret a two-way table. Several adults responded to a survey with whether they prefer the beach, mountains, or lake. The two-way table shows the results here. All right, you'll see that there's total columns here. So these are the results. So like 15 people were males who preferred the beach, 30 people were males who prefer the mountains, and so on. And then we add to find the total. So the ones in the outside here, or the margins, those are called marginal frequencies. So for example, 25 would be a marginal frequency for the number of people who like the lake. Joint frequencies would be the numbers in here because that is talking about beach and male. How many people were males who preferred the mountains? That would be these 30 people were males who preferred the mountains. How many females were surveyed? That would be 63. That is a marginal total number of females. And how many people chose the beach? That would be 55 people chose the beach. This is a joint frequency. These two are marginal frequencies. Okay, now we're going to talk about what's called the relative frequency. Relative frequency is really just the probability, but it's taking and dividing the numbers by the total. So to go from this table to this table, you would divide by the total. I would take all of these numbers, and to get to this table, what did I divide by? The total was 130. So like 15 out of 130 gives us this number here. 30 out of 130 gives us this number. And these are basically probabilities. So, we're looking at boys and girls who have siblings and no siblings, and we're looking for the relative frequency of a student that is a girl and does not have siblings. So girls, no siblings. How many students would that be? There would be 64 students who are girls that have no siblings. Now, you might notice that this two-way table is a little bit different from these because these don't have a total column. All right, so some of these you would have to make your own total columns. And all you have to do to find totals is just add them together. Okay, this would be 156 total boys. We could add 89 and 64 to find the total number of girls. Okay, the total number with siblings would be 190. We could add the 55 plus 64 would be 119. And to get the grand total, which we need to find the relative frequency, we could either add 156 and 153 or 119 and 190. Either way will work. All right, so see if you can find what the relative frequency would be. We would need to do 64 out of, if you added these up, there were 309 total. 64 out of 309, and that gives us A is 0.21 would be the probability or the relative frequency of a girl and no siblings. Okay, what is the approximate relative frequency in this table of people who were 51 to 75 years old? So we're only looking at one category here. And so that means that this is going to be marginal. It's going to be found in the margins, using the margins. And how could we find that relative frequency? There were 75 total people of that age. If we're going to relate it to the total, we need to divide it by the total. There were 251 total people, so we would do 75 divided by 251. You would get about 0.3 approximately if you rounded that. Okay, a survey was conducted to find the amount of time that each type of student spends online every day. What is the relative frequency of those surveyed who were girls who spent less than 3 hours online? This gives me two categories, so that means it's a joint frequency, and we would divide it by the total. See if you can find what that would be. The number of girls who spent less than 3 hours online would be 26 out of the total is 117. So we do 26 divided by 117. That gives us about 0.22, so about 22% of them. All right, this table shows more survey results. Employees, which one they prefer to invest in. It says, which marginal frequency is the greatest? Remember, marginal frequencies are the ones that are going to be found in the columns, in the margins, the total numbers. So our marginal frequencies are going to be these numbers here. See if you can find which one is the greatest. Out of these numbers, the largest number is 77, and 77 is the marginal frequency for 40 years or more. So there were more of those than people in any other category. Next, let's look at the marginal probability of students who preferred strawberry cake. What would that be? So the total number of students who preferred strawberry cake there were 1,032 total students, and notice it says marginal, so that's why I know it's going to be a number in the margins. Out of the total, 2,131, and if you divide that, that is about 0.48. Number 9, this table shows breakfast preferences for 360 young adults. Notice a lot of these have the total column. It's nice when they have those and we don't have to add them together. Okay, about what percent of those surveyed preferred toaster pastries for breakfast? That would be these 89 people total, this many males and this many females preferred toaster pastries out of 360, and if you divide 89 out of 360, that's going to be close to 25%. Not exactly, but pretty close. Now I'm going to give you one where we do not have a table, but we're going to need to know about a two-way table to answer this. It says, in a class of 21 students, 6 are female, 15 have an A. There are 2 students who are male and do not have an A. What is the probability that a student chosen randomly does not have an A? So again, we're going to make our own two-way table here because we have 2 categories here. We have female and male, so we have gender, and we have having an A and not having an A. Those are going to be my 2 categories. So we're going to say female and male. We're going to say having an A and not having an A. All right, so we have the categories of having an A or not having an A. We have the categories of female and male. And we're also going to have some totals. We need the totals for this as well. So we have our total, the margins here. And it says in a class of 21 students. So let's think about where in this table we could put the 21. The total is going to go in the bottom right corner of a two-way table. Everything should add to 21. It says 16 are female, so think about where that would go in this table. 21 are female, or 16 are female, that means the total number of females should be 16. 15 are students who have an A in the class, so where would that go? That would be this total here. Total, there's 15 students who have an A. There are 2 students who are male and do not have an A. So where would that go? These 2 students would be males who do not have an A. Okay, we're looking for the probability of a student that does not have an A. So we need to fill out the rest of this table. And anytime we have two numbers in a row, we can always find the third because they should add. So for example, I know that there's 21 people and I know that 16 are female, so it should be easy to find the total number of males because these have to add to 21. All right, see if you can fill out the rest of this table. There would need to be 5 males if these add to 21. Okay, and then I just fill in the rest of it. This would be 3 because these have to add to 5. I know that this would be 6 because these have to add to 21. This would be 4. And if I do 16 minus 4 or 15 minus 3, both of those should give me 12. All right, so what is the probability that a student does not have an A? That would be these 6 people out of 21 would not have an A. So 6 out of 21, if we reduce that, would be 2/7. So a probability of 2/7. Some more. This one is different. Hopefully you noticed when I changed the slide that this has decimals. So this says a teacher at a local university surveyed students to determine whether they had a job. These are the results. It is a relative frequency table. So remember, the difference between a frequency table and a relative frequency table is that the relative frequency table shows all of the numbers divided by the total. In other words, it shows the probabilities, because dividing by the total is how you find the probability. This bottom corner in a two-way table, two-way relative frequency table, should always be 1. This doesn't have the totals, but it will always add to 1 in a two-way relative frequency table. All right, so we are going backwards now from relative frequency to find frequency, and the opposite of dividing by the total would be multiplying by the total. It says 1,200 students were surveyed. So we couldn't tell that just by looking at the table. They needed to tell us that. The total is 1,200. That would be like this 130. How many students had full-time jobs? So we're going to find the total number of students, the total relative frequency of students who had full-time jobs, and then we would need to multiply that by the total to turn it into a frequency. So see what you would get for that. In total, we can see this many. These are the people that had a full-time job. If you add that up, that would be 22% or 0.22. We want to find 22% of 1,200. If you multiply that, that would give you this 264 is the actual frequency. Let's look at another relative frequency table, because it's relative because it has all of these decimals. It doesn't give us a total, but we know that everything should always add to 1. Okay, it says how many more males chose red than females chose green? So let's look at males choosing red. That would be 0.15. In other words, 15% of the people were males who chose red, and females who chose green were 0.05. It says how many more males chose red than females chose green. Keep in mind that there are 120 classmates, so we would get the percent and multiply it by 120. And what would you get? The number of males who chose red, if you do 15% of 120, would be that there were 18 males who chose red. You would multiply those. And if you multiply 0.05 or 5% of 120, that would give you 6 of them were females who chose green, and that's why the difference would be 12. Okay, let's do one more with a relative two-way table. How many more students, looking at this, keep in mind that the teacher asked 150 students, and this is a relative frequency table. That means all of the numbers have been divided by the total. It's like the probability. How many more students have internet access than do not have internet access? So we would need to find the total number that do have internet access, and that would be, if I added these together, that would be 80. The amount that do not have internet access would be 20% or 0.2. And to figure out how many actual people that would be, I would take 80% and multiply it by 150. So that means that there would have been 120 that do have internet access when I multiply this by 150. And if I multiply 150 by 20%, that would be 30 people. And if you subtract those, 120 subtract 30 means that there are 90 more students who have internet access.